Welcome, everyone. Okay, it's 8 o'clock, so class officially starts. Welcome to class, everyone. If you have questions for me, please ask. Remember, your discussion exam is tomorrow during your discussion section meeting. It will cover sections 12.1 through 12.5, so any question you have related to those topics, please make sure you ask. Okay, is someone trying to ask a question?
Yeah, I would like to ask if we get any sample exam to.
I don't have a sample at the moment because this is a different format than I've used before. So you can assume that the quizzes that you've gotten, the participation quizzes, the web assigned homework should be fair samples of the types of questions you might need to answer, okay? There may be multiple choice questions. There may be questions where you need to actually write up an answer and show your work, in which case you would have to scan your work and upload it for it to be graded, okay? Okay, the second, so there's a question about the second quiz. Would you all like to go through the second quiz right now? I can certainly do that. So let's see here. See if I can do this. Preview. So this is going to be done through Zoom. The quiz is going to be done through Zoom. All right, so I'm going to share the screen. Okay. Oh, come on. Okay. Sorry, it's just taking a second to connect here. Okay. The chat. Participants. All right, so let's go through this. All right, so first question. A and B are non-zero vectors in R3. So 3 component vectors. And we have 2 parts. We want to figure out whether the angle is between 0 and 90 degrees, or between 90 and 180 degrees, or if it's a right angle. Okay, so part A, we have A dot B is equal to 6. And our choices are that this is a right angle, it's 90 degrees, it's acute, meaning it's between 0 and 90, or it's obtuse, meaning it's between 90 and 180. So what do we think about this? Any ideas?
Would it be acute?
Okay, so somebody votes for acute. And what is your reasoning there?
It's positive, so it can't be obtuse because then it would be negative.
Okay, good. So remember, the unit circle looks like got an angle theta there measured. That's going to put you on the unit circle. At the point with x coordinate cosine theta, y coordinate sine theta. So when the cosine is positive, means you're in the first quadrant here. Remember that the dot product refers to it is related to the cosine of the angle between the vectors, and it's the smaller angle between the vectors. So if you have 2 vectors, you might think, well, there's really 2 angles. Call those theta and phi. The dot product refers to this theta, the smaller angle between the vectors. And that smaller angle's got to be between 0 and 180 degrees. So if the cosine is positive, meaning the angle is acute between 0 and 90 degrees, that means the dot product of the 2 vectors has got to be positive. Okay. And for part B, we have A dot B is equal to -6. What is going on there? Is that angle acute, right, or obtuse?
An obtuse.
So this would be obtuse. And again, you can see that because the dot product is related to the cosine of the angle between the vectors. When the cosine is negative, you have to be in the second quadrant. Okay, remember the length of a vector is going to be bigger than or equal to 0 always. So the sine of the dot product is related to the cosine of the angle between the vectors. All right, so are there any questions on that?
When would it be a right angle then?
Okay, well, do you have what you need from this page?
I'm good.
You good? All right, well. So we're acute over here, we're obtuse over here. (90° is right in the middle. When two vectors are at right angles to each other, let's call them A and B. And neither of the vectors themselves is the 0 vector, then it has to be the case that they're at right angles to each other. Right, the x component of the point on your parameterized unit circle is at cosine theta. When cosine of theta is 0, you're on the positive y-axis here, so you're making a right angle with the positive x-axis. Okay, makes sense?
Yes, thank you.
So remember that the dot product A dot B is equal to 0. That is your quick way to check. If this is true, then A is perpendicular to B, or the angle that the vectors A and B make is 90°. And when A cross B is equal to the 0 vector, that means the vectors A and B are parallel to each other. So the angle could be 0 or 180°. So 0 would mean that they point in exactly the same direction. 180° would mean they point in exactly the opposite directions. Okay, good. Any further questions there? All right, so let's look at question 2 on the quiz. We have the expression A dot B divided by the length of the vector A. And this is supposed to represent a projection. All right, so this could be the vector projection or the scalar projection. Right, those are the two types of projections that we've learned about. So that's the first choice you have to make. So what type of quantity do we have here? Is this a vector or a scalar? A dot B is a vector or a scalar?
Scalar.
It's a scalar, good. And the length of a vector is a scalar. When you divide scalars, you get a scalar. So it can't be a vector projection. It must be a scalar projection of some type. Okay, so we really have two choices. So when we think about the projections, right? Sorry. So these are our scalar projections. We use this notation component of B along A or component of A along B. So which one goes along with the ratio we have here? So it helps to think of the picture that goes along with the notation. So the way you read this thing that I'm boxing here is we're looking at the component or the scalar projection of the vector B along the vector A. Okay, and the picture that goes with that is that we're breaking the vector B up into components that are parallel to the vector A and perpendicular to the vector A. Now, let's connect the scalar projection or the component to something that we know already. Notice that when we break the vector B up into these two components, parallel to A and perpendicular to A, we can use those two components along with the original vector B to build a triangle. And one of the, that's going to be a right triangle. And one of the other angles there is the angle between the vectors A and B. Well, what do we know about that angle? We know it's related to the dot product. Now, what do we know about this component that is parallel to A? Well, the vector B makes the hypotenuse of the triangle, so the length of that is the length of the vector B. And we know from trigonometry, because this is a right triangle, that the length of this piece here is exactly the length of B times cosine of this angle theta, right? Because the cosine of this angle is the length of the nearest leg divided by the length of the hypotenuse, right? So this guy is B cosine theta. Well, I can build that in terms of something I know, that B cosine theta shows up as part of the dot product. So B cosine theta is A dot B divided by the length of A. So there's a hint in the notation, right? Component of the vector B along the vector A, that A appears sort of as a subscript. Whatever vector appears as a subscript there is the vector whose length appears on the bottom of the fraction in the definition of the component. of vector B along vector A. Length of A is going to appear on the bottom. So A dot B over A is in fact exactly the component of the vector B along the vector A. Right, so that's the scalar projection of B onto A. Are there any questions there? Everybody good? Okay, so what about the vector projection? Well, the vector projection also goes along with this. The vector projection is exactly this vector. Okay, so we know the length of the vector is this B cosine theta, which we can write as this expression. We can write the length of this vector projection as the scalar projection. So how do we get a vector that points in the correct direction and has the correct length? Well, this is the notation for the vector projection. And we know that if we want to build a vector with a certain direction, a certain length, we can take a vector that's a unit vector in the direction we want, and then multiply that by the scalar corresponding to the length we want. So that's the formula for the projection of B along A, or the vector projection, I should say, of B along A. All right. Any questions there? Are we ready to go to the next page? All right, so question, what exactly does the vector projection tell us? Here's vector B, here's vector A. The vector projection of one vector along another would be the component. So if we're talking projection of B along A, that would be the vector you need that is in the direction, in this case, of the vector A. In order to build the vector B as that vector that's parallel to A plus another vector which is perpendicular to A. So really it comes exactly out of this triangle. The scalar projection gives us the length of this vector. The vector projection gives us exactly that vector. So is that clear, everyone? Both projections can be derived from the triangle. That's exactly right. So that is probably the best way to not get confused when you're dealing with the vector projection and the scalar projection. So number one, remember what the names mean. Vector is a vector, scalar is a scalar. If you draw this triangle, remember the geometry of the dot product. You can work out all the formulas you need. as long as you remember some trigonometry. Okay, so question 3 from the quiz. So for each of the following expressions, determine the value of the resulting vector, or choose the expression, choose that the expression is meaningless. So if we have A dotted with A cross B, and we have to choose from 0 scalar meaningless or 0, 0, 0. Let's think about this. And we're told that the vectors A and B are not equal to the 0 vector, and they lie in R3. So let's build this expression up in pieces. So we have A cross B. As long as A and B are 3-component vectors, as long as they live in R3, that's well defined, and it gives you a vector in R3. And A is another vector in R3, so the dot products of the first piece and the second piece is well defined because they both have the same number of components. So that is not meaningless. So we've ruled one possibility out. Now, what do we know about the dot products of 2 vectors? Is that a vector or a scalar? So it's got to be a scalar. So this possibility is ruled out. It can't be a vector. So the answer must be 0, the scalar 0, the number 0. Well, does that make sense? So fine, it's a scalar. How do we know that it's actually 0? Okay, someone in the chat came through. So because A cross B is orthogonal to A. So notice here we've got the cross product of the vectors A and B. The cross product of 2 vectors gives you another vector which is orthogonal to or perpendicular both of your input vectors. So A dotted with something that's perpendicular to A. So A dotted with something that's perpendicular to A is the angle between those 2 vectors is a right angle. It's 90 degrees or pi over 2 radians. And the cosine of pi over 2 radians is 0. So the dot product of those 2 things is got to be 0. Okay, so that's where the answer comes from. So that was part A, and then part B, we have A dotted with B, and then we cross that with B. All right, so who wants to take a shot here? So we've got the same choices.
Is it meaningless?
Yes, and do you want to explain why?
So the dot product gives us a scalar, and you can't do a scalar cross product with a vector.
Okay, that's exactly right. When you want to do the cross product takes 2 vectors. It doesn't work on a scalar and a scalar or a scalar and a vector. You need 2 vectors, and they have to be vectors in 3-dimensional space. They have to be in R3. So are there any questions there? Okay, everyone good? Okay, ready to go on. So question 4, we've got a bunch of statements. We want to select the statements that are accurate, meaning correct. And there may be more than one correct answer. So let's write these down. So the first choice, we have A cross B. We take the length of that. And the claim is that's the length of A times the length of B times sine of theta, where theta here represents the angle between the vectors A and B. So is that correct or not correct? It is in fact correct. So good job, everyone in chat who said that. Remember that the sine of the angle between the vectors is connected to the cross product. The cosine of the angle between the vectors is connected to the dot product. So I'll do a check to mean this is good. We have A cross B is equal to A times B times sine of theta. So is this correct or not correct? So it's not correct. Do you want to explain why it is not correct?
Because magnitude of A times magnitude of B times sine theta is a scalar, and A cross B is a vector.
Yeah, that's a good argument. That's exactly right. So the magnitude of A cross B is length of A times length of B, or the magnitude of A times magnitude of B times sine of theta. You have to be careful to not drop the bars here. All right, so then we have A cross B is equal to length of A times length of B times cosine theta. And again, left-hand side is a vector, right-hand side is a scalar. So that's clearly false. The cross product is connected to the sine of theta and not the cosine theta as well. Next we have, oops, A cross B is equal to A cross B times cosine of theta. Right, so the point here now is to remember cross product is connected to the sine of the angle, not the cosine of the angle. So this is wrong. We have A dotted with B is A B sine of theta, and A dotted with B is equal to A times B times cosine of theta. So which one is correct of those last two? So the last one is correct. A dot B is a scalar, so left-hand side is a scalar. Right-hand side for both of these last two is a scalar, certainly, but the dot product is connected to cosine of theta, not the sine of theta. All right, any questions on that problem? Everyone good? All right, so last one from the quiz. We want to choose the appropriate relationship between the non-zero vectors A and B based on the result of the operations given. So in A, we have A cross B is equal to the zero vector. For part B, we have A cross B, A dotted with B, I should say, is equal to the scalar 0. So what can you say about the vectors A and B when their cross product vanishes? Are they parallel? So there's a symbol for parallel, orthogonal, or neither. Okay, so they're parallel. That's correct. And what about when the dot product vanishes? Are they parallel, orthogonal, or neither? Okay, and part B is orthogonal. Exactly. Very good. Okay, so are there any questions from the quiz therefore?
I have a question about participation quiz.
Okay,
So there was one question, but I don't remember which one, which participation quiz it was. I think it was for 5th March. I was calculating length, and I got different answer, and I don't know what I did wrong.
okay, let me see if I can find the question. Let's try a preview here. So it was the length of the curve?
Yes.
Okay, so let's see if we can do this here. So we've got this vector function. Okay, and we're working on the interval between 0 and pi over 4. So we want to compute the length of our curve that's parameterized like this. So this is your x, this is your y, this is your z. So the length of the curve is the integral from a to b of prime t. So if you think sort of in physics terms, you have a particle moving with velocity r, the length of this velocity vector is the speed vector. You integrate the speed to get, sorry, speed is not a vector. The length of the velocity vector is the speed. You integrate the speed to get the total distance traveled. So we're going to go 0 to pi over 4. And dx dt squared plus dy dt squared plus dt squared. All right, so dx dt is the derivative of cosine with respect to t would be minus the sine. dy dt, derivative of sine with respect to t would be cosine. dz by dt. If I take the derivative of natural log of cosine, I have to use the chain rule. And the derivative cosine is minus the sine. It's minus tangent of t. All right, so dx dt squared is sine squared. dy dt is cosine squared. dz by dt squared is tangent squared. Now sine squared plus cosine squared is 1. Okay. And if you remember the trig identity, cos squared theta plus sine squared theta is equal to 1. You can divide through by cosine squared to get 1 plus tangent squared is equal to secant squared. So 1 plus tangent squared is the secant squared. So this is really 0 to pi over 4 absolute value of secant. Oops. And on this range of angles, from 0 to pi over 4, the cosine is positive. So 1 over the cosine or the secant is also positive. So I actually don't care, or I don't have to worry about those absolute value signs. So really, I want to integrate the secant. And the hints we're given is that we've got the antiderivative we need there. So we don't need an arbitrary constant of integration because this is a definite integral. Right, so we'd have secant of pi over 4. It's tangent pi over 4. And then minus natural log secant of 0 plus tangent of 0. All right, well, tangent of 0 is 0. Secant of 0 is 1 because cosine of 0 is 1. 1 plus 0 is 1. Natural log of 1 is 0. So that lower limit doesn't contribute. Okay. So we're down to natural log of secant of pi over 4 plus tangent of pi over 4. Now, tangent of pi over 4 is 1. And what is secant of pi over 4? Okay, so it's the square root of 2. Someone chimed in the chat. So remember, secant is 1 over cosine. When we have a right triangle where the legs are 1, the hypotenuse will be root 2 by the Pythagorean theorem. So these are both pi over 4 when the legs have equal length. So the cosine of pi over 4 is 1 over root 2. The sine of pi over 4 is 1 over root 2. The secant is 1 over the cosine. So reciprocal of 1 over root 2 would just be root 2. And that's one of our options for the length there. Okay, so I don't know exactly where the problem would have been, but does this argument make sense?
Yes, thank you.
You're welcome. Okay, any more questions?
And can you go to the last page of a second?
Go back?
Yeah, go back.
Okay.
Yeah, it's okay. Thanks.
Okay, you're welcome. Any more questions? So we went through that quiz. So hopefully the dot product, the cross product are under control. The basics of vectors hopefully are under control, distinguishing vectors from scalars. What's important about lines and planes? Right, so we have sort of three forms for the equation of a line. Okay, so we have this vector form, which we could write out in terms of the components. We can separate and look at component by component equality. Okay, so these are called the parametric equations. And assuming A, B, and C are non-zero, we can solve each of the parametric equations for our parameter T to get what are called the symmetric equations. Oops. Okay. And what's important to recognize is that number one, we have these three different representations. You should know which is which, but you should also be able to go back and forth between them. So the vector equation, the parametric equation, the symmetric equations all contain exactly the same information. If you're given the parametric equations, you can find a point on the line by just plugging in an arbitrary value of the parameter t. So for instance, you could plug in t equals 0, and that would reproduce the point you have here that's known on the line. You could also pull off the coefficients of your parameter in each of these three equations to get the components of your direction vector. Okay, and that same information shows up in your symmetric equations. So the direction vector components show up on the bottoms of these fractions in the symmetric equations. The information about a point that you know on the line, a base point on the line, shows up on the top of the fractions in the symmetric equations. Okay, and the equations for a plane are similar. So for a plane, what you need is a normal vector, which is a vector perpendicular to any vector which is parallel to the plane or which could be embedded in the plane. So in this equation, n is your normal vector, r0 is the position vector of some arbitrary known point on the plane. The OR vector is just got components x, y, and z. That's the position vector of a different arbitrary point on the plane. So to get to any point on the plane, you can go to your base point and then find a vector that connects to any other point on the plane. All of those vectors connect to points in the plane, so they're parallel to the plane. And the normal vector has to be perpendicular to all of those, any of those. Now, if you write out, again, in terms of components, these two are basically the same equation, of course. If you multiply through, you get a scalar equation for the plane. The coefficient of x, the coefficient of y, the coefficient of z are giving you your normal vector, right? Those components in that vector show up in this form of the equation of the plane. And furthermore, you can multiply everything out. You can collect the ax0 plus by0 plus cz0. And write the equation like this. Okay, so Brooke refers to this as the linear equation, and this is the scalar equation. Both of these, in fact, are scalar equations. Both of them are linear equations in x, y, and z. All right, so I think that's where we've got to stop for today. Any last questions before we wrap up for the day? All right, have a good day, everyone. If you have more questions, I have office hours in a little while, so come back if you can.
Thank you.
Thank
Take
you.
care.
Thank you.
Thank you.
Yes, have a good one. Do you have a question, John?